will repeat some of the things which I did last time. So, variables and assignment. So, Python has 5 types of variables. We will not use much of string and list. So, we will use integer, float and arrays. Now, integers, just recap, quick recap. So, it is a binary representation in computer, within computer, and integers can be of any length, unlike other languages, it allows any length, and these are the operations. So, we will again not use this bitwise stuff in this course most of the time. So, these are examples which I had put in the last class. So, x to the 31 minus 1 will be this large number in decimal. Okay. So, you have to be careful. Today I will make a contrast between binary and decimal. So, this is in decimal. Now, if you want in binary or hex, so this is a representation you did in the homework. I think everybody is happy with it now. You can also do negative numbers, but Python will just say minus of this. The division and remainder. So, this is a division, it is an integer division. Okay. So, right now treating 5 and 3 is integer and dividing integer division. If you want float division, then you can put 5.0 by 3. So, you have to put one of them as float, then it will convert the other also to float, and it will give you 1.666. This is a reminder. These are bit operations, I think I will skip. Okay, you can just, so this and this or, it is not okay, I think it got cut. Okay, this has come here 100 or 110 will give you 110. Okay, or operation and operation you probably know from binary operation. Okay, so let us look at real numbers, which we will deal most of the time. So, there are 2 ways to represent real numbers. Now, this is not computer, right now I will just tell you the idea. In fact, this very interesting line of thought went into how to represent real numbers in computer. So, the 2 ways which we are aware of, we use the first one very often, but so this is called fixed point representation. Okay. The decimal point is fixed. So, if you write in terms of formula, then it is going to be looking like this. So, the less than 1 numbers will, so this is 1 and this is 1 by 10, 1 by 10 to the power m, and this 10 to the power n. Okay. So, with this you can represent any real number, but here my decimal point is somewhere here, right here. Okay. So, this is called fixed point representation. We use this most often in our daily life. So, let us do an example. So, in decimal number, if you have n equal to 1, so this is n equal to 1 and m equal to 2. So, what are the numbers can I represent? Now, I am limited. Okay. So, if I just have this, then I can't represent all numbers, a very limited set of numbers, and the numbers we can represent will be these. I am focusing only on positive. So, 0.00, so m is 2, so these are the 2 digits, and n equal to 1, so I can go up to 99. Okay. So, that is 99. So, these are the numbers, very limited, right. I mean, this is what you can do. And what is the spacing between 2 numbers is 0.01, but they are uniformly spaced. So, the difference is 0.01, and but it turns out that you can represent only very small set of numbers. The largest number is close to 100 and smallest number is 0.01, smallest non-zero number is 0.01, but you can do better. So, you can do better, and that is what the computer scientists thought about, and they said let us do called floating point representation. It is a fascinating representation. Now, how is it represented? It is written as the decimal part is here, but then you multiply by 10 per e. So, I am right now working with decimal, but the idea of whatever you do in decimal is same as what you do in binary, not much difference. So, we write this, so I have to ensure that a naught is non-zero. Okay, you make a naught non-zero, and then any number can be represented like this. You may need large m, but you can represent any number. Now, it turns out you can increase the range with this representation. I can get more set of range of numbers, not more set, range of numbers. So, let us do an example. I will go quickly, this is very obvious, but it is very interesting thing to notice. So, it has m plus 1 significant digits, right, because this is m plus 1 significant digits, and we need to keep some digits for exponential. So, let us do an example with m equal to 2 and 2 digits for e. So, I am again using 4 digits. So, with so what is the set of numbers I can represent. So, now my E is 2 digits means minus 99 to 99, okay. Range increased from minus 2 to minus 99. Of course, my number is 1.00, so the this part is 1.0 and 9.9, right. This is obvious. This is. Now, let us look at, are the numbers uniformly spaced in this representation? They are not uniformly spaced. So, they are uniformly spaced for one single E, but then you jump to E, go to next E, then there is a jump. So, to see an example, I like this idea, so I wanted to communicate to this this part 1.0. So, here I am making exponential, E is 1. So, spacing is 0.1 clearly. Now, when you go to E equal to 1, that means I am multiplying by 10. So, multiply by 10, then what happens? So, I have 1.0 times 10. So, it is 10, this is 11, 12. So, the number spacing has become 1. So, my spacing is not uniform in floating point representation, but I increase my range. Now, if you have the choice, which one will you choose? Of course, for computer this is the best, because I want to represent huge number of numbers, very small and very large. But even for realistic, like for physics, this is more natural. You look at nuclear scale, then you go to molecular scale, then you go to biological scale, then human scale, astrophysical scale. We always do this. We do not use, in fact, we do for our daily lives decimal as a fixed point number, but really the nature is built with this. A different scale, you need this representation. So, nature is doing this. So, it's in fact, no wonder computer we need this. Well, I mean this is a somewhat same phenomena in computer and real life, or in nature actually I would say, not real life, nature. Okay. Now, in computer how do you represent the real number in computer? Now, this is idea, but instead of 10 you replace by 2. So, that is binary. So, this is for double, this for double. So, 1 bit for sine, 11 bits for exponential, and 52 bits for precision, the decimal number. Okay. So, it will look like this, 1 for sine. So, if it is 0 then it is positive and 1 is negative, and this is b minus 1 to minus 52, this is 52 bits, and exponential is represented, whatever number is here you subtract minus 1023. So, that will give you negative exponent as well as positive exponent. So, it is very simple algebra which I will not belabor on. So, you can go from minus 308 exponent to 308, which is a big number. So, in meters universe length, universe size will be less than this, or in centimeter it will be less than this, but you have to still have to be careful. Suppose you want to exponentiate inverse size over power 10, then you will exceed this. Okay. So, you have to be careful when you do exponential, that is where you may exceed exponent. And the precision, how do I know the precision? So, precision will be the difference between two consecutive numbers. So, all the bits are zeros except the last bit when I subtract two consecutive numbers, is that correct? 52, and that means my number, the difference between two consecutive numbers is 2 to the power minus 52. Okay. This is binary. So, I have to take power with 2, and that happens to be 10 power minus 16. Okay. So, my precision is only 16 digits, anything beyond I can't represent in my computer. If you need more precision, which sometimes people ask for it, then you need to code separately. So, there are some libraries available. So, you can use, you can go to, I mean you can use, we can double this. Now, the present computation standard is double. Now, there is enough RAM, there is enough communication. So, people use standard double. If you want float, then instead of 64 bits, this is 64 bits, you use 32 bits, and 32 bits the numbers decrease. I think this probably 8 and this number is different. Okay. So, the range will decrease, but double is standard. So, use double, it costs more, the time taken is roughly double of what you need do it for float, but this is more accurate. Most people will say, well, I mean let computer do the work, you relax, and I mean let the computer is there is enough power in computer, so you can just let it work, unless there is a strong limitation of RAM or computer time. Okay. Now, so this is every, yeah, sure.
So before there used to be 32-bit operating system.
Right. Right.
Then MATLAB, for example, double precision would have to be 10 to the minus 16. Now machines are 64-bit. So does it become better?
No, what I showed here is double precision, 10 to the minus 16 with the
32-bit machine.
No, this for 64-bit machine. This for 64-bit operation. Now, okay, what has happened now? This is technical part. Presently, the number of wires which come from the CPU to RAM, there are 16 wires are coming. So it can access 16 bits at a time. Earlier, the number of wires which would come out was 8. So you could get only 8 number, sorry, the 32, not 8, 32. So 32 was more convenient and fast, but now 64 wires are coming. So say double is standard. That's why they say we support double operations. If you're doing 32-bit, then this precision is 36 or 37. This number is 37, not 308.
Now, even with 32-bit, it used to be 10 to the minus 16 MATLAB.
No, well, MATLAB is doing some work, additional work. So Python allows you to use as many numbers, as many accuracy you like. Okay, you can.
MATLAB is not doing anything extra. It's 64-bit.
Yeah, MATLAB is using some C libraries within, which is 64-bit. Okay. So this is standard. Python will be doing this, but if you want more higher precision, Python will take care of it, and that's why Python is slower. C will optimize for a uniform set of data. So Python and MATLAB happens to be slow because it allows you flexibility, but then it can't optimize it. Okay. Okay. So now everyone knows how to convert this. This is simple operation, but let's just look at one number, 1.1 in decimal. I want to represent in binary. Now, how do I do it? So, one is I will keep, so one is, remember the first A naught is 1, 1 is, that should be non-zero, and only one non-zero number for binary is 1. Okay. So, you do not store 1, this one is not stored in the computer, this one, first one. Second one is stored, so you multiply 0.1 into 2, so this is the operation, 0.1 into 2, so 0.2 is less than 1, so it is 0, the first bit is 0. So, this standard stuff, no. So, suppose I want to get the decimal of 1.35. So, get this off, multiply this by 10. So, 3 will go to the left of decimal and you pick that, that is the first digit. Multiply by 10 after that. So, that will be 0.5, this is taken. So, this multiply by 10, then you get 5. So, that is how you get the digits. So, you do the same thing here, you multiply by 0.2, 2, then 0.2, 0.4. So, these are all zeros, these are all zeros. Here I get 1. Is that okay? But I request you to please do this. These are simple stuff, but you should be able to convert one to other. Okay, this was done thousands of years back. So, you get 1 here, then 0.6 is remaining. So, again keep multiplying, they get 1 here, and do this. Okay, and that is how the number I will get is 3 zeros here. Then 1 here, 1 here, then again there is 1 here, then 2 zeros. So, you do this. So, this is the binary representation of 1.1. It turns out it will not stop. That means 1.1 cannot be represented accurately in a computer. Decimal, yes, 1.1 is, again 1.1 is possible to represent using 2 digits, 2 decimal digits, but not with binary computer. Here you see is a recurring digit. So, this will recur after 0.2 it will recur, no. So, it is a recurring, and it cannot be represented accurately in computer. So, these are problems many. So, there is called round off error. So, computer has rounded off a number 1.1 I thought was could be represented accurately inside the computer, it cannot. 1/3 of course, we can't represent accurately in decimal itself, and the same thing happens for binary. So, you can play around with these numbers, it is fun, but I will not spend time here. So, this is how you get the float hex. So, 1.1 float hex will be exactly same number. and 1.5 can be represented accurately inside the computer. It is 1.001, sorry 1.10, 1.1 is 1.1 in binary, because 1 by 0.1 will be 1 by 2 and 1 by 2 is 0.5. Yeah. This one plus x AP power I think power is 0, this power is 0. So, if this power is 0, exponent is 0, okay, exponent, this is exponent part. How do you convert? Okay. So, let us look at it here, this is simpler. So, how do you get 8? So, 8 is coming basically, so the number is 1.1 all zeros like this, there are 52 of them. So, here 52 I have to start pairing. So, how many 4? So, hex is 4, no, x is 4 bits. So, 4 into 12 is 48, right. So, 48 bits will be units of 4, but the last 3 is not units of 4, 3. So, this should not be there. So, there will be a lot of zeros here. So, this is, so here 14 into 13 into 4 is 52. Okay. So, it comes in bunch of 4. So, this is 8, this is 8, 2 to the 3, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and rest all zeros. That is why we have 1.8. Okay. Now, here why I am writing 1, so here you see this first 4, this is 1, okay, so that is 1. Now, rest all is, this is 9, right, this is 9, so 9, and this repeats, 9 will repeat. So, this is hex, this one is hex and this is binary. So, I write 2, that is binary. Okay. Computer will print hex, hex is more convenient, no, otherwise 52 digits you do not want to write. Is that clear? Okay. Okay. So, let us do it 3.0. So, 3.0 you have to write, so 0.3 into 10, 3.0. So, let us just convert. So, actually you have to convert 3 point int, no 3.0. So, you have to, no, you have to convert to binary. So, that, so this is 2 to the power. So, basically you want to write 3.0 as some number times 2 to the power exponent. Okay. Now, you have to, so 3 will be, so I have to, I can of course use the computer.
101.
101 is it?
11.
11, but I need a float representation. Okay. So, float representation I need to do, so 1, so this is going to be, so 2 to the power 1, 2 to the power 1 you take it out, and then is going to be 1.5. Okay. So, so this is how you will represent. So, this is going to be 1.1 into exponent will be 1, 2 to the power 1. So, check in your computer, this is how it should happen. Okay. So, the exponent is in power of 2. So, complex float. So, Python will allow float operations, a complex float representation is very simple. You write the number as real plus imaginary j, 1 plus 1 j, and you can do operations with that. So, I can square a number, so x square, this x square is 2 j, you can verify this is it. Now, multiply by a number, absolute of x, conjugate of x. Okay. So, it is very useful if you are doing quantum mechanics, it is very useful to do complex operations, okay, and it is trivial. Okay. Next is strings. We do not use very often, but computer scientists use all the time. In fact, everything is manipulation of strings. I feed in my program, right now this computer is manipulating string. displaying it and all that. It's just a string manipulation. So, how is string represented? So, take variable x and you just say within double quotes or single quote, double quote are interchangeable. So, x is this is string. Okay. So, this is a variable, x has a value, this string is stored in x. So, please keep in mind, if you are not used to computing, when I say x equal to something, it does not mean I am equating it, this means I am assigning to x. Okay. This is not equal operation in math, the assignment operation. So, x will get this assignment of the full string and store it, we do not need to worry about how it stores, it stores. Now, when I say, so in this is straight from Python. Okay. So, I just cut pasted. So, in is input and out is output. I do not have different colors on this string, I just cut pasted in this keynote. So, this will you will get exactly same on your computer. So, when I say x means I am asking what is x, and the answer is this is string. Okay, we will come within quotes saying that it is a string. Now, I can add something to that string, this is called concatenation, you can concatenate. So, I add something to string. So, x plus you just say any string. So, now the new string which is bigger string is this string high string. Okay. So, you can add string, you can delete string part of it. So, all that operation can be done. We will not do this in our course, we do except for input output. Okay. So, input output is we need some communication with the computer. So, it is very easy. So, one standard way to output a variable is print. You can print it on the screen and also you can print to a file. Okay. That I will not discuss right now. You can print numbers to a file or put numbers to a file, that part I will discuss later. I mean, if a large arrays weather data, so you want to put it in a file and that will be done later. Right now, you can output a number x equal to 5 is a print x. Of course, one simple way is to just say x, it will give the value of x, you do not need to print. So, output is for print as well as you can store it some file, but file part we will do later. For input, some homework may have this kind of exercise. So, you can so this in, so you can put in the computer x equal to input this, and so what will come out at the bottom will be this without this equal to, then you could put a number 10 and it will go in and store in x. Okay. But of course, one simple way is to do what, put x equal to 10. So, in Python you do not need to worry about input output, the C you need to worry about it, but it is a interpreted language. So, I just say x equal to 10. What really is meaningful is to operate on data, large data input, well not very large data, but data, let us say 1000 numbers, that you need to read from a file, but that we will do later. Okay. So, x is already there. So, this part you have to enter, you enter it from your keyboard. So, we may give homework saying well put some number and do something on it. So, that is how you can do it. Okay. The next is important thing which I will just cover for completeness is called list, which again we do not use in physics, but computer scientists use it more often. This is a collection of objects, a list is collection of objects, and these objects could be of different types. So, some could be integers, some could be real, some could be string. So, one example is I missed a file, is it? So, 1 2 high. So, this is 3 numbers 1 2 high, and actually I did seem to so this is a string, this is a list. So, my list is y equal to 1. So, you put within brackets, within this square brackets 1 2, and the 3 elements 1 2 and high. Okay. Now, 2 integers and 1 string is allowed. C will not allow this, but Python allows it. And how are they stored? There are 3 elements 1 2 high, and how do I access it? So, I can access by saying this is 0th element. So, Python indexing starts from 0, not from 1. So, Fortran starts from 1, but C does from 0, and Python also, Python and C have very similar array operation. So, it starts from 0. So, the indices are index, to catch something you need to get the roll number. So, these are roll numbers for this object, but roll number starts from 0. Why 0? Anyone can, I mean, it is very obvious. Why should not we start from 1?
Why don't we store?
No, it's 0 is more natural. Okay. So addresses are generated, like address is again a binary number. So the first number binary is 000, all zeros. So that is an address, it is a valid address. My house number is 0, it is a valid address. Okay. So that is so when you start that creating the addresses, you start with 000, then 0001, like that. So 0 is the first number for address, and it is, that is how it starts. So C started this notation, and the address is 0, first 0. So 0, then 1 and 2. You can also say from minus. So minus 1 is the last element. So minus 1, minus 2, minus 3. So you can go from the right to the left. So I can access it using yi. So these are what I printed. So y0 is 1, y1 is 2, y2 is high, and y minus 1 is high again. So this is an illustration, it works. Okay. So you can access, if the last element is y minus 1, you do not need to say, if you do not know the size, it is very useful. You can also get the size of this array, not array. So the list, y is the list, called len, length. Len of y will give the length. Now here this is in square bracket. Okay. So access is by square bracket, and when I say so all the function calls are with small brackets. So arguments will go in small brackets. So you have to be careful with what you are using. You can delete an element. So I can delete y1. So y1 will be second element, not the first element. So if you delete the y1, then what is left is 1 high. Okay. So you can do these operations with list. But list is, since it has any kind of elements are allowed, any type of elements, it is not very fast. So what people have done, so I will just tell you a few more operations with list. You can, if you say star 2, it does not multiply because it is not integer or float. So it will just double it. So you can see that there are 6 elements and this doubled. You can add a new element, 10 is added in this. Append, so append is, I appended 2 elements, 3 in computer. So append is very nice operation, and you can pop, you can basically access. So this pop is access. So pop 2, third element, pop 2 is third. No? So this is a confusion, you have to get used to 0, 1, 2, that is. So these are operations for the list. We can do slice. So we can get part of the list, not full list, but part of the list, which is useful. So this is tricky part. Okay, this is confusing. So I just want to spend a bit of time on this. So India has 5 characters. So I am storing it as a string. So it has 5. So x equal to India. So it has 5. So if I say x0, it will be 1 I, x4 will be a. Now if I, so I can access it like what I told in the earlier slide, but I want to get a bunch of them one shot. So if I say 0 colon 3, what should I expect? So you should expect 0 to 3 or 0 to 2, and the way to understand this is for the range, this is called range operation. The range operation is not starting from the middle, range operation is starting from the wall. So India is stored, this stored with these are boxes and there is a wall of the box, you know. So this index is the wall index, not the index of the house. So it is the wall of the house, you know, wall of the rooms. So so this is 0 is the first wall, second wall, third wall, fourth wall. So I say what is contained between 0 wall and third wall, and that will be IND. So if you think like this, you will get it right. So you have to just, so the range object is a slightly different than indexing, and that is the convention followed in Python. I mean why they did it I do not know, but this something was starts and then this continues, you do not want to change it. So, range is also an operation, range is also a function, range. So, you can give 0 to 3, it will give you 1 to 3. You can also say range 3, that is the same thing as 0 1 2. Okay, range 3 is not 0 to 3, 0 to 2. So, this is about list. Now, we will come to arrays, and this is called NumPy arrays. So, what is NumPy? So, NumPy is numerical Python. Okay. We focus on NumPy can do various things, but we will just focus on NumPy is a array of numbers, integer and real, and this is what we will use in our course. We are going to focus on NumPy arrays. So, this is example of NumPy. So, how we write NumPy array? Now, you should not say y equal to 1 bracket 1 comma 2, that will be a list. So, array is a library. Now, I will just make one more remark, that when we say Pylab, IPython minus minus Pylab. So, Pylab imports various libraries. Okay. So, one of the libraries it imports is NumPy, numerical Python. So, it has very rich operation on arrays, which I will show you some of it. So, if I say 1 colon 2, that is a list, that is part of standard Python, but NumPy has, you have to say array within brackets. So, this is the argument of a function called array. Array is a function, okay, with coming in square in a small bracket. Fine. So, this is it will this is same objective as list, except it will be fast and is limited to numbers. For our course we will just stick to numbers. So, you should use this, not 1 comma 2, because many operations will not be allowed on list. Like if I say y star 2, you saw that it is not multiplying the by the elements by 2. I wanted to multiply by 2, but this will do it. So, if I just say y star 2, then it will multiply each element by 2. Okay. So, this is quick, no? If you wrote in C, you have to make a loop. So, this does in one shot, this multiplies by 2. You can get the size of the array, or you can say length. This, I prefer this is preferred, okay, length len y. You can add a number to each element. So, y plus 3 is adding to each element of y a number 3. So, it will give you 4 comma 5. So, this is useful operation which you will need to do later. We can also create a 2D arrays. So, 2D array will be you put bracket then another bracket within. Is that clear? So, this is 2D array. So, there is a square bracket here and here, then there are 0 1 and 1 0. So, this is what matrix is it? Not identity. 0 1 1 0. So, it is a 2D matrix 0 1 0 1 1 0. It is an array for computer, it is an array. It has elements 0 1 1 0. So, if I say x, then I will, so this I should not have done. X is, if I want to know what this x is an array with these entries. I can get the determinant of x. So, x it will treat as a matrix one shot and determinant is minus 1. I can get the eigenvalues of x and eigenvector. So, say Ig(x), so eigenvalues of 1 minus 1 is correct, and the eigenvectors are two of them are this, okay, 1 minus 1 and 1 1. So, let us do another example. Y is array 1 comma 2, z is 4 5. I can take a square root of y. Square root of y is you will take square root of each element. So, it is going to give us 1 square root 2, and I can add these two arrays, just do plus. So, it is adding element by element. Most of the operations are element by element. So, it will do this operation element by element. Slicing can be done with NumPy arrays as well, and you can also create element array with 4. Now, sometimes I do not know the entries, but I just want to create a array with size 4. So, I can create, in fact, I use most of the range 0 is 4. So, you will create an array with 4 entries which are zeros. A range 0 to 3 is very useful. So, it is going to create from 0 to 1 2. This is like range, exactly a range, but it is a NumPy function. You have to put A in front. Ones is all ones, empty is the zeros. So, these are same as this. We can also very useful function called linspace, linear spacing. So, this is example. I want to create NumPy array with 9 elements which are equispaced from 1 to 2 inclusive of 1 and 2. So, what is the difference between the consecutive numbers? 1 by 8. So, these are the entries 1, 1.125. So, linspace is a very useful function. I can create an x axis with linspace points. Okay, so append. Yeah. Appending here, NumPy arrays size is fixed. You can't append as far as I know. NumPy arrays you can't append. NumPy arrays append will not work for NumPy array. You can't add an element in that. So, you have to start. You can start with a list. Now, I may be wrong in this. So, you can start with a list, append, then you can convert it to NumPy array. So, you can convert a list to a NumPy array, so that is what I did at one point. So, that I will show you in the next class. I will do that. So, is that okay? Just one. So, let us answer his question first. So, linspace is, so the three arguments. First is the starting number, second is the last number, and how many points will be there including these 2 points. So, there are 9 points. So, how many? So, you create a size of the array, create an array of size 9. So, that is the third argument. Okay. So, I want a size 9 array with 1 and 2, and all the elements must be equispaced. So, this is the answer. Okay, one more question. Yeah. So, you can put, like for example, here this will treat as integer, but it will convert it to float if required.
All entire combination of string.
For NumPy array, not string. String as well. String is possible, but I have not worked with that. But you can put. So, I can say y equal to 1 comma 1.1. This is like what you want. So, this is fine, but it will convert 1 to 1.0. It does something inside. You can do the type. So, I am not sure what that is. D type. So, to get a type we will get this. Is integer, float. So, right now it is storing as integer and float, but when required it will change. So, Python is not strict typing. So, type will be changed according to the need. Same variable y, or let us say, so this is example. I think I will not start the next set of slides. I can say 5, then same x I can put 11.0. So, right now x is integer, but now it will become float, same x, okay, which is not allowed in C. So, you can't store a float number in an integer. I could also do a string. So, it is not a strict typing. So, that is why it is easy to program, you do not need to worry about types, but also it is inefficient and prone to errors also. No? So, some variable you thought it is 5, but somewhere you made it 11.0 or string. So, you need to be careful. Typing is very useful for large codes, strict typing. One for efficiency, second is errors. You do not do errors. Now, this part I will not delve into it. Okay. So, following typing is useful, but Python the power is because you do not type it. Means you understand what is integer, float, string, they are called type, what type of variables they are. And Python says, well, I do not care, I will use whatever is assignment, it will, the type of the variable will be of that type. Okay. So, next class we will start working on the structure of the control structures in Python. So, you can do if loops. Actually, I have 2 minutes. So, but I am going slow, actually I should go a bit faster. So, you can do if, while loop, for loop, you can write functions. Now, there will be homework based on that. So, I will assign the homework, but Monday I will cover hopefully all of it. It is very simple. So, you can do if statements, for statements. So, you need, so any language will have 3 structures. So, one thing is of course, these are called simple structures. So, set of statements one after the other. Second is branching statements. So, you need to take a decision. No? So, if something is true, then you do something else, do something else. So, Python will have this branching thing and repetitive. So, something repeating. So, it should allow, so I should not be writing for I equal to 1 do this, for I equal to 2 do this, for I equal to 3 do that. So, it says for I equal to 1 to 10 do this. So, this is called loops, and the other important thing is called function. So, something you want to use again and again, like sine function. So, I do not want to be writing that set of lines to compute sine of 5, then for sine 15 or sine 1.5, you should not be writing this again and again. So, you write a function which you can call whenever you need it. So, these are constructs we need it for this course. So, this I will do in the next class.